Hi everybody, this is lecture 18 and today I'd like to tell you to wrap up the material for the second midterm. So I'll tell you about divergence and curl in 2D and 3D. So last time we learned about div and curl in 2D. Today I'll mention the 2D case again and show you what div and curl mean in 3D, and I will also explore flux in 2D. So all these things appear in Green's theorem, so I pre-prepared and wrote down Green's theorem on the slide, so we can revisit everything all these definitions from last time before I give you more new material. So, but in any case, I want to show you a few examples of, I want to show you one example of integrals, using integrals and Green's theorem to compute the flux, and tell you about div and curl in 3D, and then give you a criterion for when a vector field is the div of a function or the curl of another vector field. When a vector field is the gradient of a function or the curl of another vector field. All right, let's get to it. So, so here on the left you see Green's theorem, the two vector versions. Green's theorem rewritten in vector notation in two different ways. So let's recall what everything is here. So first off, one of the main players is the vector field. Here is a 2D vector field. It has components P and Q. So the other main player is the curve C, right? So we have our vector field F and we have our curve C. And our curve is, well, for the first theorem, it's supposed to have the counterclockwise orientation. So this means that the unit tangent should be going in the counterclockwise sense throughout the whole curve. So in the second theorem, we have this t times ds, so the unit tangent times the arc length element on the curve. So on the first theorem, the orientation appears explicitly. So in the second theorem, we don't talk about t times ds, we talk about n times ds. And here, for the second theorem, we want the outward unit normal. So we want this normal rather than this other one. Right? If I tell you that a vector is normal to the curve at a point, this only leaves two possibilities. And here we want a vector here we want the outward normal. All right. So the other main ingredients are the div and curl of f. So the curl is the thing that we've been working with most of the time. So the curl is just the x partial of the second component of the vector field minus the y partial of the first component of the vector field in 2D. Right. So this is a function in 2D. We'll see that in 3D, the curl is another vector field. The divergence of the vector field is just the sum of the first partial of the first component plus and the second partial of the second component. And to connect these these vector version formulas with these formulas using vector notation with the ones we had before using component notation, we can just use a few dirty tricks using differentials, but which they're strictly speaking illegal, but they have enough truth in them that the notation is sufficiently friendly that you're safe using these sorts of calculations. So t times ds is the same as this vector of differentials dx comma dy, which we sometimes also denote by dr. And so we have the dot product over here. This is just p times dx plus q times dy. And down here, n times ds, as we last saw, if our curve has the counterclockwise, or if we're using the, well, never mind, the orientation doesn't play a role. So here we just want dy comma minus dx. Yeah, well, I take that back. So for this minus sign to be here, we need the curve to have the counterclockwise orientation. Otherwise, it could be on the other side. Okay, so let's do now some terminology. So I talk about flux. So here's Here's what mentioned flux before. So here's what flux is. So this number over here, this line integral, is the flux of C. Oops. Flux of the vector field F through the curve C. Okay. Since we're using the outward unit normal to compute this line integral, this is the outward flux. Flux of F through C. So this is measuring how much this is measuring how much the vector field aligns with the outward normal as you go around the curve. That's why. So if F is mostly points out of the curve, so if you go around this curve C and F is always pointing out like this, here it's going in, right? But if it's mostly going out, if most of the time it's going out, then the flux will be positive. That's why we talk about outward. We won't revisit this again, but just for the record, this other integral where the normal is replaced by the tangent is called the circulation of the vector field. All right, so let's compute a few flux line integrals, right? So integrals of the form f dot n. Or actually, before we calculate it, let's look at it a little bit closer. So let's understand what flux is. So flux. So here let's keep our color code. So the curve is red, the normal is blue. Right? Let's look sideways. Here's our curve, and in blue is the normal, the unit normal vector. Okay. And let's look at the value of the vector field at this point. It's going to be something like this. Okay. So the thing we're integrating is f dot n times ds. Here I'm going to replace ds by delta s, a small piece but not quite infinitesimal piece of the curve. Okay, so delta S is going to be this over here. I guess I'll draw it. Well, we have red already, so just do it in black. So this is ds. Okay, so I have a little piece of the curve. We have a vector field in the F and the unit normal. So here's what this number is. Let's to understand this physically, let's look at the situation where the interpretation is clearest. That's the case of fluid mechanics. So F, let's say, is the velocity field of a fluid. So the fluid velocity, right, just tells you how fast the fluid is moving at each point. So we have a 2D fluid, and there's this imaginary curve, and we want to know how much F is crossing that curve. Is it crossing from this side? Oops. Is it crossing from this side to that side, or the other way around, or is the fluid not really crossing the curve at this point? It's just tangent to the curve at the point. Let's see. So let's wait. Let's look at the fluid that is on this little region and wait 1 unit of time. Right? If I wait 1 unit of time, if I multiply velocity by 1 unit of time, just get the distance that the object moves in that unit of time. So here, if I wait 1 unit of time, I'm going to get a little tower of fluid. Right? And okay, but what's the area? So what's the area of fluid that crossed delta S in this unit of time? Well, it's the velocity. Well, it's the height times the area of the base. But the height is just F times. Oops. The height is just F times dot product the unit normal. right? If you will, we are doing here, we can say that we have an angle theta here, and this is the length of f times the length of the unit normal, that's 1, times cosine of theta. And then you see that this height is really this dot product. Okay, so f dot n times ds just gives us the height of the tower times the base. That's the area of fluid that crosses delta S per unit time, in 1 unit of time. Okay, so in conclusion, if we have in the fluid situation, if we're the sort of integral, so if we have a curve, let's say here's our curve, right? When we're giving it this normal over here, right? Remember, there are 2 choices of unit normal. So in Green's theorem, we always, so for the theorem to hold, the assumption of the theorem is that the curve is equipped with the outward normal, but in general, we could, the notion of flux makes sense for either choice. And there's, vector field. And this vector field is the velocity of the fluid. So in this situation, if I wait a little bit of time, some amount of fluid will cross this curve, and the amount, well, the area of fluid, here we're talking about a 2D fluid. That's why we talk about area to measure amount. But in 3D, we'll see we'll have volume. Anyway, so the area of fluid, so it's exactly the same little paragraph over here. So this integral is just giving me, actually, let me move this down, is giving me the area of fluid that crosses not delta S, not this little piece, but crosses the whole curve per unit time. So you see, this number has a very concrete, very nice interpretation. And if we quickly go back to Green's theorem, the second version, which involves flux, this is telling me that if F is the velocity field of a fluid, then the area of fluid that leaves this region C, this curve, leaves the region D per unit time, is the same as the double integral of the divergence inside the region. The divergence is the rate of change of expansion. It's the rate of change of the area of individual pieces of the fluid. Sorry, it's kind of, so if I take a little piece dA inside D, and then the derivative, the amount of the derivative of its area with respect to time is the divergence at a point inside. Right, so this tells me how much this is increasing. This is telling me how much the fluid is expanding, and on the inside, and that has got to match, according to Green's theorem, the amount of fluid that crosses the boundary curve. Okay, so let's do an integral using the language of flux. Let's set up an integral. So here's our example. So for our example, our vector field, the vector field will be xy plus sine x cosine y. And the second component will be minus cosine x sine y. All right, and our curve will be nice. It'll be just a square, or rather a rectangle. Okay, so there's our rectangle, and so our curve has 4 sides: C1, C2. Oh, the orientations are not important here, so it's just C1, C2, C3, and C4. And we would like to know, improve the picture. So C, our curve C, is just all 4 sides. And we would like to know the flux of the vector field out through C. Okay, so what is this? Right, so we wish to know, really, the integral over C of, so we have the vector field and we have our curve, and we just want to compute this flux. So we want to know, this is just asking us for the integral of f dot n times ds throughout our curve C, where n is the outward normal. So I'll just, here's n, here's n, here's n, and here's n. Here's n on that side. Okay, so one way we could do this is just perform 4 line integrals, one over each side, and then you have to figure out what n is on each of these sides, what f is on each of these sides, parameterize the 4 sides, compute ds for the 4 sides, and then you evaluate the integral. But it turns out that here we have a closed curve, so it's probably easier, it's probably better, and in fact it is better to use Green's theorem. So let's see. So here, let's just use Green's theorem. According to Green's theorem, this single integral I can compute as the double integral on the region inside the curve, right? So here's the region inside the curve. Of the divergence of our vector field multiplied by dA. So this is the normal version of Green's theorem. Now let's see. So our vector. So what's the divergence of this vector field? Well, the first component. So let's see. So this here is the first component of the vector field, and this over here is the second one. So the divergence, recall, is just p, the x partial of p. So this is p sub x plus q sub y, right? So the x partial of p is just y plus the derivative of sine x cosine y with respect to y is cosine x cosine y. Plus the y partial of q. So the y partial of q is just cosine x, minus cosine x cosine y. Okay, good. So you see, this is really an in-class demo where things, can miraculously cancel to help the instructor. Okay, so we computed the partials, and this bit cancels with this bit. So we just have to compute this flux. We just have to integrate the function y over this rectangle. I mean that I can do pretty quickly. So here, let's say, I never told you the sides, the width and the height of the rectangle. So the width is 1, and the height is 4. So we do need those numbers. We do need so the answer is going to depend on these numbers. So the width is 1. So let's integrate x from 0 to 1. And y from 0 to 4, and then the function we're integrating is y with respect to dy dx. That's the integral for x from 0 to 1 of y over 2, y squared over 2 between 0 and 4 times dx. So this thing over here is just 16 over 2, that's 8. And 8 integrated with respect to dx from 0 to 1 is just 8. 8 times 1, which is 8. So that's our final answer. So the flux of our vector field, of this vector field f around this, out of this square is 8. Right, so if f was the velocity field of some fluid, this would mean that 8 units of area, let's say we're measuring areas in meters, and that we're measuring time in seconds. Right, so this would mean that 8 meters squared of fluid are leaving this rectangle in one unit of time, in 1 second. So 8 meters squared per second. So the flux of f through this curve, through this rectangle, out of this rectangle, is just 8 meters squared of fluid per second. Okay, let's now move on to the second part of the question. So the second part of the question is not as easy. It's not going to let us, just get off, get away without computing a line integral. We're going to have to compute a line integral. The second part asks us about the flux of f, not through the whole curve, but only through the first 3 parts. So we want to know the flux of f through C1, C2, and C3. Okay, so that's what we want to know. And so in principle, we would have to compute the integral. So this integral over here, this sort of integral, but instead of doing it over the whole curve, we just have to do over the first 3 sides. So that would mean setting up 3 integrals, 1 for each side, and so that's some amount of repetitive work. But it turns out that there's a smarter way to go about this, especially, well, because we've already computed the flux through all 4 sides. We already know what the integral over all 4 sides is. If we just want it over the first one, here's what we can do. We can take the answer we know for the integral over the 4 sides and subtract the integral over C4, and that will give me the integral over the first 3. So the flux out of all 4 sides minus the flux through the first 3, minus the flux through C4 gives me the flux through the first 3, which is what we want. And then computing the flux through C4 is just going to be a single integral. So let's do that. So the integral over, so this is the same as the double integral, the integral over C. So here's the flux through all 4 sides minus the integral through C4, through the last side. Right, and the point is, we've already computed the first one, that's 8. Now so let's look at, so let's ask ourselves, what's the integral over C4? Let's now work on C4. So let's look at C4. So here's C4. C4 is just a piece of the y-axis. So we need a number. We need to parameterize the y-axis, and to parameterize means to describe points in this curve, this line segment, using a single number, and the y-coordinate is the obvious number in this case. So our parameter will be the y-coordinate, and x will be 0 for all points because we're here, right? So on C4, we're going to describe, so x is 0, y is, well, itself. So our parameter will be the function y, and the bounds, so the parameter will go from 0 to 4. Okay, our vector field is x times y, but x is 0, so that's 0 plus, let's do everything here. So that's 0 times y plus sine of 0 times cosine y. So we just get the first component just becomes 0. The second component is minus cosine of x. So remember, on this side, x is 0. So this is just minus cosine of 0, which is minus 1, times sine of y. And the unit normal is, well, okay, so can we figure out the unit normal on this thing? It's just going to be, it's just, this one I can sort out visually. Right? This one is just a minus 1, 0. So there you have it. So this is, the n for this side is just minus 1, 0. It points, the normal on C4, it just points to the left. Okay, so you know what? So I can also compute ds, that's fine. So ds is, you know, square root of dx dt. It's going to be 1 times dy, right? Because this 1 is really square root of dx dy squared, that's 0, and plus dy squared, that's 1. So square root of 0 plus 1, that's square root of 1, which is the one I wrote over here. But the point, we really don't need, we in fact don't really need this ds, because no matter what ds was, you can see from the first 2 stars that this is always 0, right? This dot product. So f is, so the normal, so the vector field f, this vector field on the side C4 is always pointing up or down. I mean, there's a sign there, so sign could be positive or negative, but in any case, it's always a multiple of the vector j, whereas n is a multiple of I, so the dot product is always 0, and so the integral of over the side C4 is just 0. And so the integral for the first 3 sides is the same as the integral over all 4 sides, that's 8. So that's the answer for number 2 as well, for the second part of this problem as well. Okay, so let's now make a few quick remarks about div and curl in 3D. So divergence and curl in 3D. Okay, so let's say f is our 3D vector field. So I change, so this f is not the same as this f. Maybe to signify we're changing subjects, let's move to a different slide. So now we have a brand new f, and it has components p, q, and r. So p, q, and r are functions of x, y, and z. That's our new vector field. Let me just tell you what div and curl are for such a vector field. So the divergence of f is just, it's the easy one to remember. It's the x partial of p. So the x partial of the first component plus the second partial of the second component. Second partial of second component plus a third partial of third component. Okay, so that's a function that we build out of our vector field. The curl in 3D is more interesting. Well, it's interesting because it's different from what we've seen. So in 2D, div and curl were both functions. In 3D, div is still a function, but curl is now a vector field. So another vector field that we built from the original one by taking derivatives. So the first component, and now it's like a soup of partials. So the first component is dr dy. So here I'm looking at my notes on the side, you can probably tell. Second component is dq dz. Sorry, second part of the first component is this. And then the j component is dp dz minus dx dr dx. And then the third component of the curl is just dq dx, is the one that we're familiar with, dq dx minus dp dy. Combination of partials we're familiar with. Okay, so this formula is nearly impossible to remember. Okay, now that I challenge you, you're going to tell me that it's actually possible to remember this. There are patterns in here. For example, you see that in the I component, so that's the first component of the answer, we just involve the second and third partials and the second and third variables, and they're mixed, right? So third component R of the vector field is differentiated with respect to the second variable, and the second component of the vector field is differentiated with respect to the third variable. So they're, and the same holds true in the other cases, right? So for the J component of the curl, we're looking at so the second component of the curl, we're looking at first and third components of F and variables X and Z, and so on, and the partials are mixed and so on. Okay, so you could remember this, but probably you'd make a mistake with the sign. So here's a much better way to remember these definitions. The trick is to think of the gradient as a vector. But this is highly illegal. Okay, so you should not do this in public. I mean, except when you're teaching and telling people that it's illegal. So, I mean, I'm here to help you and tell you the best way to do things. I'm not really a bureaucrat. Anyway, so the way to do this is you think of the gradient as a vector, right? So you think of the gradient, imagine the gradient as this vector with partials, whose first component is d dx, second component is d dy, and third one is d dz. Right? This is illegal because, I mean, we know how to talk, so the standard thing, what people know right away what you mean is if you talk about vectors whose components are numbers, maybe even complex numbers, but still numbers. Here, instead of numbers, we have, operations. So derivatives are things that take functions to functions, right? They're differential operators. So we don't want to make too rigorous sense of that. Let's just, for sake of argument, pretend these operations were numbers. And then if we did the dot product, so then we could compute the divergence of the vector field simply by taking the dot product of this fake vector with our vector field. Right? Can you see? If I took the dot product of gradient with F, I would get x partial of first component plus y partial of second plus z partial of third. That's exactly the divergence. And the curl would have a very compact formula. It would just be the cross product of the two. Right, so this is perhaps the best way to define and work with these things. Right, so remember the cross product of two vectors is another vector, and you compute it with a funny determinant. I'm going to do an example in a second. And doing the cross product of this and this, you're going to get exactly this thing as an answer. Let's do an example of let's compute curl for a vector field, so we know there are nothing to be scared here. Okay, so we have a vector field, and the components are x, z, x, y, z, and minus y squared. So this is our vector field. So then in this situation, the curl of this vector field is just the cross product of the gradient, this gradient vector with the vector field. So the result is so we compute this cross product with the determinant. So that's here's how you compute here's how you compute that. Just use I, j, and k. Put I, j, and k in the first row, and then you put the second vector in the second along the second row. So here are the components of the gradient. And finally, here are the components. You just put in the components of the thing you're integrating on the last component. So that's x, z, x, y, z, and minus y squared. So let's compute now this determinant, right? You go do this, and then you go back like this, and that with a minus sign. So another way to do the same thing is to expand by rows. You just do I times this determinant. Let's do that. So let me just finish telling you what you do. You do I times this determinant plus j times, and then you do the determinant backwards. Rather than doing this, you do the other way around like this. And then k, you do this determinant over here. So the first component, it's I times, so the answer here, this determinant is I times this minus that. So the y partial of minus y squared, that's minus 2y. And then minus ddz of xyz, that's x times y. The second component is j times ddz times xz, that's x minus ddx of y, that's 0. And the third component is k times ddx times xyz, that's yz, minus ddy of xz, that's 0. So that's our answer. You see, it's just something you can do without thinking twice. Differentiation is a very mechanical thing, even when you soup it up with fancy words and like curl and stuff like that. Okay, good. So the last thing I'd like to tell you today is, so we now have these derivatives of vector fields, right? Div and curl are really derivatives of f, and so when we have a function, it's always true that function is the derivative of another function. You can build another function whose derivative is your given one. That's not the same for vector fields. And if I give you a vector field, well, it could never be the divergence of another one, because the divergence of another vector field is a function rather than the vector field is started with. So, but it could be the curl of a vector field, or it could be the gradient of a function, right? So if it's the gradient of a function, we've been through this, the vector field is conservative. So let's briefly look at this question. So when is the vector field the gradient of another one? So here's the theorem, and I'll just state it. So let's say f is a vector field in R3. So defined on all of R3. And so in this situation, the curl. So it turns out that there is an easy way to characterize vector fields that are gradients of functions, and that we've seen. So we saw before. So I gave you before the condition for a 3D vector field to be the gradient of a function. I gave you it in terms of 3 equations. Turns out I can say that's a single equation if the equation has 3 components. So I can rewrite those 3 equations in this form. Right, so the curl is 0 if and only if there exists a function f such that, let me just say, call it by the name, function f such that the given vector field is the gradient of that function. Okay. So this theorem is giving us a test. It tells us that we can recognize that our vector field is the gradient of another function, of some function, by checking that the curl is 0. And this is a familiar I had mentioned this before, but using a different language. Instead of saying that the test was that the curl is 0, I said that the test was that we had three equations between the partials that had to be true, right? But it turns out the equations were that qx had got to be equal to py, p sub z had to be equal to dr dx, and that r sub y had to be equal to q sub z, right? So just saying these three equations are true is the same as, I mean, saying the curl is 0 is saying that those three equations are true. So this is, the first part is not new. So I only proved, so I did give you a good idea of the proof of this. So I did show you. Let's remember where we are. So I did explain to you last time or in the past that if there is a function, then for sure the gradient is 0. I didn't tell you that when the vector field is defined on all of R3, you can actually go back and just from the knowledge that the curl is 0, you can conclude there is a function. So I gave you a pretty good argument in 2D, but I never fully explained this in 3D. But you can trust the theorem and use it. This is going to figure in the homework for this week. So the reason I put it here is because I want to state the other result. So that other result is telling you what happens. So we have two derivatives of vector fields. We have the derivative, the curl, and we have the divergence. So here we understand what happens when the curl is 0. Let me tell you what happens when the divergence is 0. So if the divergence is 0, well, for vector fields defined in 3 dimensions, sorry, for vector fields defined in all of R3, then the divergence is 0 is 0 if and only if f is the derivative not of a function but of another vector field. If and only if, let me tell you the bottom line, 1, 2, 3, maybe 4 lines down, if and only if our vector field is the curl of another vector field. And now here's the full language. So there exists a vector field A such that our given vector field is the curl of that vector field. So so in the first situation we say that the vector field f is conservative, and we know how to exploit that using the fundamental theorem of calculus. Just because integrating the gradient of a function is really easy, you just evaluate the over a curve. You just have to do that. You just have to evaluate the values of the function on the endpoints of the curve and subtract, right? So so this is good. So we're in this situation, we have extra knowledge of the vector field, and we know how to exploit that already. We still don't know how to exploit this. So Stokes' theorem is a theorem that will tell us how to integrate curls of vector fields, how to simplify, how to leverage this knowledge. But we still haven't gotten there. So this may seem a little bit it may be unclear at the moment of why this is helpful, but on a high level, I just want to say that if you know a vector field is a derivative of something else, there's probably a theorem that'll help you. I mean, in this case, there is a theorem that'll help you to integrate f over surfaces. We'll get to that in a moment. We'll get to surface integrals after the midterm. But point is that there is value in knowing, there's usefulness in knowing that your vector field is the gradient of another one, is the curl of another one. Okay, so let's just check let's just check implication number 2. So let me just look here. Let me prove the easy implication here. It's just a calculation. It's good exercise. So let's say here I'm saying that f is the curl. So let's say that A, normally P, Q, and R are the components of f, of the vector field f, but here I never said this, so I can just, you know, use those letters to denote the components of A. Otherwise, I'd have to come up with letters for the components of A. So the curl of F, so F is the curl of A. So we want to know what is the divergence of F. Well, this is the divergence of A. Sorry, the divergence of the curl of A, but the curl of A, let me find the formula. It's R sub y minus Q sub z. Second component of the curl is PZ minus RX. And the last component of the curl is QX minus PY. Oh, that one I didn't have to check. Okay, so this is, so let's see, so the first component, when you do the divergence, you just take the curl of the first, sorry, you take the first partial of the first component. So here, first component is here, so if I take the first partial, the x partial, get ryx minus qzx. And then you do the y partial of the second component, so you get pzy minus rxy. And finally, you do the z partial of the last component, so that's the last one. If you take the z partial, it gives you qxe minus pyz. Okay, and I claim, so the theorem is telling me, so this implication of the theorem is telling me that this is supposed to be 0, and it absolutely is, right? You can see the cancellation. So here, we're always, so in this class, we're always working with vector fields which are continuous and have continuous partial derivatives. So these components, they satisfy, they have, so they satisfy, I believe, what it's called Young's rule, namely that their partials are symmetric. If you take a partial with respect to, so here's, so for example, pzy is the same as pyz. So you get this cancellation. And similarly for R and for Q. Let me use different colors like this so you can see what cancels with what. And so you do get 0 as the theorem says. So this is just to say, this is just to illustrate a calculation, to show you the calculation that gives you this implication, which is the easier one. For the other one, you need a more serious argument, but we're not getting into that. Okay, so this is what I had to say today. Thanks so much for listening, and I'll see you guys next time.